So now we investigate why we can use a weaker failure detector than P. And we start gradually. If you remember the hierarchy of failure detector, then there was one failure detector weaker than P, which we call the strong failure detector. If you recall the strong failure detector, it just says it has strong completeness. Eventually, every failure is detected, but it has weak accuracy. Weak accuracy says there is, if you remember, weak accuracy says that there exists a correct process which is never falsely suspected by any other process. There is one well-connected process. So, roughly speaking, S is like P, but accuracy is with respect to one process. So in fact, the algorithm that we just described still works with a strong failure detector. And here is how to show this. If we go to validity, take the same algorithm, you always decide on own proposal or some adopted proposal. So that is easy. If you go to integrity, so round increase monotonically. So each node decide only once at the end of the algorithm. This is the last round, basically. And termination is still the same because every correct process make it to the last round. The failure detector S is still complete. And if the leader is correct, the validity of the best ever broadcast, it ensures delivery, and therefore we can move to the next round. So let's look at termination then. So in this case, uniform agreement, which is no two processes decide differently. So take an accurate, correct leader. So S always is correct with respect to that leader. And we call that leader I, the ID I. So weak accuracy says that there exists such leader. And termination says that we are going to get to that leader. So that leader will come in and have a round to run. So such process exists. And what it's going to do, it will best ever broadcast V. Every correct process will get V and set its local variable, its proposal, to V. And then in the end, xi is V in all subsequent rounds, so the final value is V. So as you can see here, we can weaken our failure detector to S, and we can still use the same algorithm to achieve uniform consensus. In the next lecture, which is the Paxos lecture, we are going to see an algorithm that uses the eventually perfect failure detector, or equivalently omega, the eventually the election, to achieve uniform consensus.